All right, we're recording. So, Nick, just making sure that you're okay with us recording this and posting it to YouTube.
I am, and in fact, making it available under a Creative Commons Attribution license, CC BY 4.0. So have at it.
Awesome. All right, so thank you everyone who's here today, especially those who are returning after coming to part one of Nick's tutorials yesterday. Nick is a research software engineer who does all kinds of fun things, particularly with the Plasma Pi project, and works at the Center for Astrophysics, and is going to tell us all about writing our first software test with pytest. Take it away.
Thank you, Mel, and I'm happy to be here again for a two-part series, the second of two. And as I think Dimitri mentioned earlier, these are being posted on YouTube as well. So today we're going to talk about writing our first software test with pytest. And if there were two Python packages that I would recommend scientists to learn, the first would be NumPy, and the second would be PyTest. Software testing is that important. So um, let's start with some motivation. Why do we write software tests? The obvious one is to catch and fix bugs, and preferably as soon as we introduce them. When we write code, we're inevitably going to introduce bugs, and software tests really help us find them sooner rather than later. Software tests also help us provide confidence that our code is giving the intended results, which are hopefully also the correct results. Software testing makes our lives easier. Um, a lot of the time as scientists, we write tests or we test our code manually. And this is okay for really small projects, but it doesn't scale up, and especially when you have a bunch of interconnected parts. So having automated software tests really does make our lives easier. I wish I learned it about 17 years before I did. There are also some other reasons to write software tests. Software tests can help us track bugs that maybe we don't have time to fix now, but we want to fix later. Software tests can also provide examples of how code that we wrote is intended to be used. So it can serve as a form of documentation, though not the primary form. And overall, the main reason why I write software tests is so that we can change the code with confidence that we are not introducing hidden bugs elsewhere in the program. You might have uh, uh, a thought in your mind that writing tests makes code rigid, that it's harder to change code with tests. But in fact, when we have well-written tests, it makes the code that we write more flexible. So without tests, changes might introduce hidden bugs, and we're less likely to change code because maybe we'll break something somewhere else in the program and we won't know about it until decades later or weeks later or something like that. But with good, clean tests, we can find out right away, as soon as we run tests, if a change broke something that is already being tested. And with good tests, we can also track down bugs more quickly and also isolate bugs. There's a saying that from a book, Working Effectively with a Legacy Code, that Michael Feathers defines legacy code as code without tests, which is a little scary. And by this definition, I've written a lot of legacy code in my life, though I've been working on it since. So tests really do help. I want to define unit tests in particular. There's a spectrum of tests, and unit tests are the essential building blocks. So unit test verifies a single unit of behavior, does it quickly, and does it in isolation from other tests. And this is a definition from a book, Unit Testing Principles, Practices, and Patterns by, I think, Korokov. A fun book to, fun audiobook to listen to during a pandemic, it turns out. All right, and I think that's the, oh yeah, what is PyTest? So PyTest is the most widely used testing framework for Python. And what pytest does, what it includes, it runs tests. So it's able to go through a directory and files in a directory and figure out which tests need to be run and then runs them. And it provides a whole bunch of testing tools and capabilities, a lot of um, testing infrastructure. And pytest also makes some significant improvements on error messages, especially with the search statements. And I'll get into that a bit later. So I am going to close this um, and, oh no, disconnected. Okay, I think it's working now. So we'll go to the live coding part of this tutorial. And is the font size okay? Okay, I have at least one thumbs up. All right. So I'll scroll back up and I'll post. Oh, thank you, Dimitri, for posting the links in the chat to the installing UV and to this tutorial site itself. So if you want to follow along, please install UV. This is the topic of the tutorial yesterday. And we're not going to use too much of it, but it's going to greatly simplify a few things, like being able to create a skeleton of a Python package in one command. So, all right. So if we open a Unix terminal, let's create a directory to work in. And this will make it easier to keep things isolated. And so we can delete the directory afterwards if we want to. So let's make dir pytest tutorial. And then cd pytest tutorial. All right. So one of the things that we're going to use from yesterday is creating a virtual environment. And if you weren't here yesterday, a virtual environment is an isolated space where we can work on our Python projects separately from the system installed Python. And we can create a virtual environment, in this case, to make sure that everyone has the same environment that we're working in. So let's do uv env dash dash Python 3.13. We don't strictly need to say which version of Python we're using, but to make sure that everyone is using the same one, we'll specify it. And so this command will create a virtual environment that is located in the .venv directory. And we can activate it with, in my case, this command. But if you're using PowerShell or a different shell besides Bash, you'll probably have a different command to activate it with. So in my case, I'm using Bash, the Bash Unix shell. And so I'll take this command and type it out. So source.venv/bin/activate. So now we're using, the prompt has changed. So we're using the pytest tutorial virtual environment. So now we can install the packages that we'll need, and we only need 2 of them this time. Let's do uv pip install pytest and numpy. And uv installed that really quickly. So one of the benefits of using uv. So we have numpy and pytest and a few different dependencies. So before we go into writing a software tests, we're going to go through some of the testing infrastructure, some of the Python infrastructure and NumPy infrastructure for writing tests. So let's use Python. And the first thing that we're going to do is try out an assert statement. So these are, a lot of you have probably run into this before, but if we write assert true, nothing happens. But because we're asserting that something is true and true itself is true. But if we assert false, then we get an assertion error. And it says that points out the thing that's false that um, is supposed to be true. And we can use assert to compare different objects in Python. So we can do assert 1 equals 2, and that's false. So it gives us an error message. We can assert 1 is not equal to 2, and that's true. We can assert 1 is less than 2, which is also true. And what do you get when you multiply 6 by 9? So we can say 6 times 9 equals 42. This is not quite a direct quote from The Hitchhiker's Guide to the Galaxy, but it's fairly close. And we find that it is false. So 6 by times 9 is not equal to 42. We can also include an error message for when the assertion is false. So let's do assert, let's create two lists, 1 comma 2, and we want to assert that that is equal to 3 comma 4. And now we can write an error message that list contents are unequal. And when we assert that, it's false, and it prints out the assertion error, the message that we provided. Error messages are incredibly important. I don't want to say anything otherwise. There was one code that I used where occasionally the simulation would spit out 200 or so matrix inversion errors, like unable to invert matrix. And it took me a little while to understand that when that happened, it was because the density went negative, and so the simulation ended up crashing. But in this case, it had a lot of less specific errors and didn't say what the actual problem was. So it's really worth putting a bit of extra effort into error messages, especially if it's something that other people are going to use or change, or that we're going to come back to a few months from now. So in Python, Python has some specific ways of handling truthiness. So different objects in Python can be considered truthy or falsy. And we can figure out which ones are truthy or falsy by using the bool statement. So we can try, for example, bool of 1, and this ends up being true, while bool of 0 ends up being false. Collections in Python end up being considered truthy when they are non-empty, and this includes strings. So if we do bool of a non-empty string, it will say true because the collection, the string, is not empty. But if we do bool of an empty string, it's going to be false. So strings and lists and sets and tuples get treated as true if they contain items and false if they are empty.
Nick, some of your typing is starting to go off the bottom of the screen, just so you know.
Oh no. Okay. Is this a little better?
Yes.
Okay, cool. That up a little bit. Thank you for bringing that up. That is very helpful. Also, everyone should feel free to ask questions. I have the chat open, so if you ask a question in the chat, I'll be able to get to it very quickly, and I might be able to see if anyone raises their hand also. All right, so let's continue this and try empty and non-empty lists. So in Python, a list is enclosed in square brackets. So if we do bool of an empty list, it gets treated as false, but bool of a list that contains things is treated as true. All right. So these are two of the building blocks for tests. Another is Python's exception framework. So an exception is an error that happens when Python code is being executed. And one example of that is if we do 1 divided by 0, and we get a zero division error. So the exception name is zero division error, and it very helpfully says division by 0. This is a good variable name because it says exactly what it is, what the reason for the error is. So I always appreciate good variable names. We can also raise our own exceptions. So we can raise a value error. And in this case, it says value error because we just raised it. And we can also include error messages. So let's raise value error. And we can add error messages here too. And it shows up value error, and it has the error message that we included. And we can be as descriptive as we need to be with this. So I'm not going to cover how to handle exceptions gracefully. But if you're not familiar with try and except blocks, they're really helpful for if you want to handle these exceptions gracefully. So if you run into a zero division error, you can do something for that specific case and be able to like have the program continue on as you want it to. All right. So now we'll get into the very dangerous floating point comparisons. And in software, numbers besides integers are represented as binary, and they have a finite precision. And because of this, we can have situations where if we assert 0 plus 1 plus 0.2 and say that is equal to 0.3, this in plain English or plain numbers, plain math, should be true, but it's false. And the reason is that 0.1 and 0.2 are, if you add them together, they're not exactly 0.3. They're very, very close to it. But the finite precision of computers can't handle it. So if we do 0.1 plus 0.2 minus 0.3, then we get that it's 5 to the negative 17. So really tiny, but it's enough to make these things not equal. Another really important tool, this time within NumPy, is numpy.isClose. What numpy.isClose does is test whether two floating point numbers are close to each other or not. So let's import numpy as np, the standard abbreviation, and do numpy np.isClose. And the first thing we want to compare is 0.1 plus 0.2. And we want to see if that is close to 0.3. And it says true, yes. 0.1 plus 0.2 is close to within a tolerance of 0.3. There are certain keywords that we can use to numpy.isClose. So if we can do numpy.isClose 10.0 and 11.0. So we want to see if 10 and 11 are um, comparable to each other. And we say the ATOL, or the absolute tolerance, is equal to 1.01. And what this is saying is that um, this will return true if the two values are within 1.01 of each other. That's true. But if we switch it to 0.99, so numpy dot is close 10.0, 11.0, ATOL equals 0.99, we get that as false. We can also specify the relative tolerance between two numbers. And we can do things like that for np dot is close 10.0, 11.0, and then the relative tolerance, rtol, equals 0.1. So they're within 10% of each other. And this is true. If we wanted to get the specific mathematical definitions for ATOL and RTOL, we can go to the docstring of numpy.isClose. To compare lists and arrays, we need numpy.allClose. So we can do ones equals np.ones, 5. And so this will create a NumPy array with 5 elements that are all 1. And then twos equals 2 times ones. And that's an array of all twos. And so we can compare these, assert np.allClose, ones, and twos. And this will give us an error message that these are not, in fact, equal to each other, or not close to each other. There's at least one element in the arrays that is not close enough to the corresponding element in the other array. NumPy.isClose and NumPy.allClose are two of the most common functions that I've used in writing tests. So these end up being really important. One thing to note is that if you're using AstroPy units, which PlasmaPy does, there are corresponding functions called astropyunits.isClose and astropy.units.allClose. And these compare quantity objects which have units. So if you want to compare 5 meters to 5.1 meters, you can use these functions within AstroPy. So now let's move on to not a number values. And these are things which end up being helpful to have, but quite annoying, because if we say np.nan equals np.nan, that's false. So to do that, there are a couple of ways. Oh, I forgot to mention that we can get nan, not a number values, when doing things like dividing 0 by 0 in a NumPy array. A question. Do the AstroPy comparisons work across units, like comparing 5 meters to 0.005 kilometers? Yes, they do. They might have a check in there to make sure that they're the same units, but I think it will pass if by default if you compare things with different units, which makes it really handy. So that's a good question. Thank you for that. If we do np.isClose, np.nan, and np.nan, again, it ends up being false. But there's an equal nan keyword that we can use, np.isClose, np.nan, np.nan, and we'll say equal underscore nan equals true. And in this case, it finally works. If we want to specify, or if we want to check that something is nan, isn't not a number, you can do np.isnan and then np.nan. And this also will return true. So nan values do come up occasionally in testing, and they can also cause headaches. So these are important things to keep track of. Okay, so we're fine. We've gotten through the pre-testing essentials, the building blocks of tests, and we can now write a software test. So let's exit Python, EXIT. One side note is that with Python 3.13, you no longer have to put exit in parentheses. With parentheses here, you can type exit all by itself. I was pretty excited about that. So upgrading to the most recent version of Python, um, right now it's 3.13. I highly recommend for that and better error messages all around. All right, so this is a side thought. Let's, oops, make sure that pytest is working. So in this case, we have pytest installed, 8.4.1, the most recent version. And if you need to, I'll copy the link from Dimitri again in case you need in the chat for the installation instructions and things like that and the tutorial. So we'll use UV now to initialize a Python project. And UV is magical because we can do this in a single line. So let's UV init a project called double. And so it initialized a Python project called double in the double subdirectory. And if we did this manually, it would probably take about 20 minutes. So UV is really helping here. So let's do cd double and see what's in it. And if you're using PowerShell, you'd use dir instead of ls-a. And we see a few different files within this, which we talked about in detail yesterday. The main one that we'll be dealing with today is main.py, which is what contains the Python code that we'll be using. And another one is pyproject.toml, which is the primary configuration file for a Python project. So it's setting this up isn't always trivial. So UV makes it easier so that by creating it automatically. All right. So now we're going to open main.py and create a function that we want to test. And I'm going to use a text editor called Nano, which comes installed with most shells. I think it's also in PowerShell. But as long as you're using a plain text editor like I think Notepad++ or Emacs or VI or Vim, these will all work, or your favorite integrated development environment or IDE like PyCharm or VS Code. But I'm going to use Nano because you can use it right in the terminal, and it probably works on your computer as well if you're using a terminal. So let's open main.py. And in this, we already have a main function, which we're going to ignore. And let's create a new function called double of x. So double is a function of x. And then 4 spaces, return 2 times x. So in main.py, we now have double, which doubles a variable. So I'm going to exit Nano by pressing Control X, and it says save modified buffer, and I'm going to press Y, and then file name to rate, right? Main.py, and enter. And if I want to see what's in main.py, I can do cat main.py, which is short for concatenate. So main.py now has a function double of x. So now let's write a software test. So let's do nano test underscore double dot py. So this function over here. And in this case, we want to first import the thing that we're going to be testing. So let's import main. So main is the file that contains double. And let's write a test. So def test doubling 1. And then 4 spaces. And assert main.double of 1 is equal to 2. And this is a test that if things are working correctly, if we double 1, we should get 2. So I'm going to press Control X again to exit and press Y and enter. And now we can show test double .py, and it contains this, this function. So test doubling 1. One important thing to note is that pytest needs us to include tests in files that begin with test underscore. And it needs tests to be the names of tests to start with test underscore also. So if you want pytest to find it without doing anything special, precede everything including tests and test themselves to start with test underscore. In an earlier version of this tutorial, I mixed this up and it took me about like 2 minutes to figure out what I had done wrong. So starting things with test underscore is important. It's also really helpful to use the names of tests to describe what is being tested. And in this case, I have a slightly long function name, and it's test doubling 1, and it says exactly what the test is testing. So long names for tests can be more helpful than short but abbreviated names. I often say measure the length of a variable name, not by the number of characters, but by the time it takes to understand what the variable means. All right. So now we have a function to test double in main.py, and we have a test doubling 1 in test double.py. So let's write pytest. Right. There's a bit of a lag, but hopefully things will work. So we just ran this test. So what this output is saying is that it's running on Linux for the most recent version of Python and pytest, and it's running it from this directory. It found the configuration file for the project, and it collected one item. It found one test, and in test double.py, it ran one test as denoted by a green dot, a period, indicating that the test passed. And it said one test passed in 0.01 seconds. So now let's add a test that intentionally fails. Let's do nano test double.py. So nano test double.py. Let's go to the end of that and say def test that fails. And in this case, we do assert main.double of 1. And let's say we want to make sure we want to assert that it is equal to some large number. And this test should fail because if you double 1, you're not going to get 7.89e. I don't know how many that is. Now we have a test that fails. So this one. And we'll control X and Y and enter again. And now let's run pytest. And in this case, it says it collected 2 items. And in test.py, it has one test that passed, the green dot, and one test that failed, which is the uppercase F. And under failures, it has it shows a description of what went wrong. So in test that fails, this is the name of the test. We asserted that when we double 1, we get 7.8 E14. I don't know how many that is. And pytest ended up evaluating this main.double of 1, that got 2, and 2 is not equal to this. So, um, so we have an error message here. So there are also some additional text here, and it says function double at 0x7f da 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 da. And what this 0x stuff is the memory address of the function double, which is essentially like where the function is stored in memory. And this can be helpful rarely, specifically when you have functions that might have the same name, but are defined in different places or something like that. And for the most part, we can ignore this information without any problems. But another case is that if you're working with lambda functions, so if we create a function called triple, let's say that lambda of x, so a function of x returns 3 times x, that can be helpful to make sure that things are found, especially if you're creating like a bunch of lambda functions. All right. And we didn't include an assertion error, so it doesn't include the assertion. And at the end, it has a short test info summary in test.py, test.fails failed, and it has a shortcut for the assertion. This one test failed, one test passed in 0.04 seconds. All right. So these are software tests, possibly your very first one, so congratulations. And now we'll go through a few tips with, actually, make sure this is up to date. Thank you for your patience. I just made a few updates at the last minute, which is always fun. I want to make sure that they got right. Okay. So there are a few software testing best practices that I do very highly recommend. The first is to keep unit tests short and focused on a single behavior. For the most part, each test should test one thing, or possibly 2 or 3 very related things, but for the most part, test one thing. This is usually good advice, but occasionally you'll need to write longer tests to make sure, for example, that the program as a whole is working. And those can be known as integration tests or what's the name for it? I think system tests. My mind is blanking, but it's probably system tests. End-to-end tests. Yes, end-to-end tests test the whole program. And And there's a spectrum that unit tests test specific things and are really helpful for finding bugs and isolating bugs. And integration tests and end-to-end tests, longer tests, make sure that different parts of a program work with each other. Another tip is that if you have code and you're finding it hard to test, it's possible to rewrite the code or refactor it to make it easier to test. And one of the strategies that we can often use for that is to write short functions that do exactly one thing. Another strategy that I sometimes use when I remember to is called test-driven development. When we start writing tests, we often start by writing the function that we want to test first, and then after that, write the test. In test-driven development, we write the test first, and then write code to get the function to pass the test. And test-driven development is helpful a lot of the time because it forces us to decide how we want our functions to behave before we even start writing them. So it's a way to think before we code. And it's not always the best approach, but it's a good thing to have in our toolbox. All right. So I'll pause again if there are any thoughts or questions that anyone wants to share. And I'm also taking a look in the chat and don't see anything. All right. You can go ahead. Also, thank you all for being here. I really appreciate it. I like sharing about software tests because they're so important. I really want the broader Plasma community to start making software testing to be a core part of what we do. All right, so let's move on to a few more PyTest techniques that we can use to more customize tests. All right. And we're going to use what are called decorators. And I'm not going to go into it in much detail, but a decorator is a function that operates on or wraps another function. So decorators can be used to change the behavior of functions or change how a function is invoked. And in this case, the decorators that we're going to use are not really going to change the test, but more add some metadata to them. So to tell PyTest what to expect. So occasionally we want to skip a test. So let's do nano again, test double.py. So nano test double.py. And at the bottom, we'll write another test, def test to be skipped. And we'll, in this case, raise our own exception, raise a value error, and let's say this test was not skipped. So this test, as written, will fail, and we'll get an error message that the test was not skipped. To tell PyTest to skip it, we first have to import PyTest at the top, and then we will decorate this with pytest.mark.skip. So now in this example, this decorator, which is denoted with an @ is telling PyTest, this test is marked to be skipped, so we shouldn't run this test. And I will close this, Control X. Okay, one moment. The platform is lagging again. Okay. So I Control X. Yes, I want to save the modified buffer and then enter. And then I'll do cat test double.py. so we can see what's there. So we added this function. Now let's run pytest again. And it again ran quickly. And since we have this test, it's now denoted with a lowercase s that is yellow. So it collected 3 tests in a test double.py. There's one test that passed, one test that failed, as we intended, and one test that we skipped. And then it goes back to the error message that we had. And so it's one test failed, one passed, and one skipped. All right. So that's pretty handy because sometimes we write tests and they're for behavior that we're going to use later on, but we don't need yet, or that we haven't written yet, something like that. But if we have a test that we're writing, for example, we found a bug and we don't have time to fix it yet, but we want to write a test to keep track of it. We can use pytest.mark.xfail, which is short for expected to fail. All right, so let's open nano test double.py again and go to the bottom. And then let's do f test that, let's rename it x fails. And in this case, let's make sure that it fails. So assert false. And as written, this test will fail and will be recorded as a failing test. But we can say pytest.mark.xfails. So we can decorate it with this. And now pytest is saying it's okay if this test fails. So it will be recorded as a failing test. So now that we have this function in here, I'm going to do Control X, Y, and enter, and run pytest again, and enter. And okay. So in this case, it turned out to be failing, which is not what I intended. So there is something that I did wrong. And usually that is a typo. And I'm going to open, first thing you need to do when you get an unexpected error is to take a deep breath. So nano test double.py. And it turns out that this should be xfail instead of xfails. So I'll remove that extra character, Control X, Y, and enter. And now I'll run pytest again. Okay, and things worked as expected. So we ran pytest found 4 tests, collected 4 items, 4 tests. First passed, the second failed, the third we skipped, and the fourth we x-failed. So it's not counted as a failure, but as an expected failure. And it doesn't show up under the list of failures. So it's a way to keep it marked that the test is failing, but that it's expected to fail. And this is something that can be used, for example, if you have a network test that needs an internet connection, but the internet connection is flaky. So that's one possibility for using it. Or if you have a bug that you don't have time to fix now, which is usually how I end up using it. All right, and the last thing we're going to do is to parameterize tests. So let's do nano test double.py. In each of these cases, we tested one thing, it would be a giant pain and not very good programming to write a separate test for every case that we want. So test doubling one, test doubling two, test doubling not a number, test doubling infinity. For those things, um, it would end up being like hard to read, hard to change, and just overall cause headaches. When we parameterize tests, we can test multiple cases using one test. So let's start by writing a test. So test double, and then I often like to write it as the argument as the first variable and expected result as a second. And in this case, the test is taking arguments, which we haven't provided yet, but we'll get to that in just a moment. So we can assert main.double of argument is equal to the expected result. And this should be fine so long as we're not using floating point numbers, which we would use numpy.isClose for. All right. To parameterize it, we use the pytest.mark.parameterize without an extra e here. And then this ends up being a function. And the first argument is going to be a string that contains the name of the arguments that are being parameterized. So the first one is called argument. And the second one is going to be expected result. So that's a string. Next, we want to create a list, and we want to create pairs of the argument and the expected result. So if we want to test that doubling one, that should equal 2. So let's write pair argument and expected with expected result. And let's start with this. So in this case, we're doing the first argument, the first item in the list. I'll give it a moment. And right now, it looks like a lot of work to say that we're testing that doubling one is equal to 2, but it lets us add more cases to test. So I'll do Control X and Y and enter. And then we can run pytest. And in this case, it has the extra test, and that ended up passing. So it's all well and good. So let's go back to test double.py and go down to the very end again. And now let's say we want to 8 spaces, test that 2, when you double 2, it's equal to 4. I'll just tab. That we double 4, let's double 4 and we get 8. And then double -1 to get -2. And 500, double that to get 1,000. And then let's add one test that intentionally fails. So if we double 1, we're not going to get 561. And let's mark that as an intentional failure. All right. So in this case, we have one test function that we're able to use for a whole bunch of different arguments and expected results. So if we double 1, we get 2, double 2, we get 4, and so on. Right. You can exit this and then run pytest again. And in this case, we'll scroll up a bit. It had a green dot for each of the cases that passed as expected, and then a test failure for the failure that we expected. In this case, it says test double, and the two things that were provided with it were 1 and 561. And it's printing out like what the values are. I think that might actually be a recent improvement to pytest, so cool. Um, and then it has like the list of things, and it goes through for the specific case and says double argument to, and that ends up not being equal to 561. And so there, we're with this setup, we're able to test a whole bunch of things at once. And this is one of the pytest um, tools and techniques is that I end up using really often. I was really happy to learn this. There's kind of a distinct improvement in Plasma Pi's tests from before to after when we learned about pytest.mark.parameterize. So it's really helpful. The syntax of this is kind of hard to remember. So it's helpful to go back to like look at PyTest documentation and um, see what it is, and then like copy like an example and then extend the example. All right. Then I think I'll show a few quick command line options. As with most Unix commands, if we do run pytest with dash dash help, we can get a whole bunch, like way too much helpful information. So that was with pytest help. And I'm going to press Control C so we don't execute that again. There's also a way to run a specific test. So pytest, and let's do dash K, and let's do test that fails. And in this case, it found this one test that intentionally failed. And this is helpful if you have a lot of tests that take a lot of time to run. And one that I use very often is pytest TP equals short. And what this does, the thing that print here, sorry. So when you get a chain of exceptions, like a value error caused an assertion error caused a whatever, that's called a traceback. And the reporting for that in pytest can be kind of long. So we can do pytest tb equals short, and that will often shorten the error message. In this case, there's not much to shorten, but tb equals short can make the pytest results easier to see. I think, oh, yes, yes, yes. One last command, do Control C again. Pytest dash dash show locals. And when this happens, show locals ends up printing out what the values of different variables are. And this can be really handy if you want to get a bit more information about what's going on or something confusing is happening. Right. And that's all I was planning on going through. Just a little over, actually about exactly an hour. So awesome. We did good. And I'm happy to take questions now, and if there are thoughts that you want to share or insights. And I'm happy to stick around for a little while after too, in case anyone wants to chat. So thank you, everyone.
All right, let's thank Nick with our virtual claps or live claps for their presentation. I'm going to stop the recording here, but feel free to continue asking Nick things.